All right, welcome back to our exploration on what might be our last transformation on parabolas. The good news about all these transformations is that those concepts will translate to more advanced graphs and future courses to come beyond algebra. The skill required to be able to understand this concept is to be able to sketch the parent linear graph and to be able to transform it with a different slope. Not only be able to graph it, but understand how it transforms the graph, all right? So let's practice that right now. And maybe you can do it on paper or visualize what in different colors what it would look like. I will do my best possible job to do them as quickly as I can. And I've color coded them in green. I'm going to graph the parent graph. So slope of up 1 and over 1, up 1 over 1, up 1 over 1. I'll do that 3 times. Then I will get this point. All right. And by symmetry, we will have this point down here. So hopefully you can see those connect, and let's see how that looks with my straight line. There's y equals x, okay? In yellow, I want to now try and sketch the graph of y equals 2x. Y equals 2x also starts at the origin, but has a slope of 2. So we're going to go up 2 and over 1, up 2 and over 1 2 times will give us that point right there. All right, and by symmetry, down 2 over 1, down 2 over 1. And the question to think about is which one of those two graphs is increasing the fastest? Obviously, it must be the y equals 2x. We can see that already. So another way to think about it is how did the parent graph in green transform to the one in yellow? It's one of the questions we're going to keep in mind today. And lastly, in blue, I'm going to sketch the graph of y equals 3x. Y equals 3x also goes through the origin, but has a slope of up 3 and over 1. Guess we'll just go with 1 point here. But that's enough to visualize which of the three is increasing or how did one graph transform to the other. All right, by symmetry, I think I'm looking for this point here. All right, and is that what you expected this system of equations was going to look like? What is happening as the slope gets becomes a larger number, like 2 or 3 or 4x or 5x? It's going to become steeper. Hopefully you can visualize that. That's the main idea here. All right, and another question I think is how did the green equation become the yellow one? Notice that they all have something in common, however. They all go through the origin. So the only thing that happens is that it seems to have gotten larger. For the green one to become the yellow one, it seems like it got larger. It got multiplied by some number. What number did it get multiplied by? By 2. That's the main idea, right? And because they're all going through the origin, how did the green one become the blue line? All right. How did the green one become the blue line? It was multiplied. It seems that it got larger. Must have been multiplied by something. What did it get multiplied? It's by a 3. All right. That's the main idea to think about. So I want you to think of equations in the form y equals some number a times x. All right. Think of the a as a coefficient, not a 9. All right. The variable is x. All right. So these are in the form y equals x. In the previous courses, you may have seen it as y equals k times x for direct proportionality. And in Algebra 1 earlier, before quadratics, we saw this form as slope, the slope form, y equals, where n represents the slope, and the k represents for algebra, and the k represents the constant of proportionality for pre-algebra courses. And one more way we can interpret that is by thinking about it as a transformation, the way we want to visualize. How did it get transformed? It got stretched vertically. Hopefully you can see the y values from the green to the yellow are being stretched vertically, all right, because they share the same y-intercept. So that's the main thing to start thinking about. All right, great. So let's look at a different example of that and apply that same type of thinking to parabolas now. Notice how we started with a parent linear equation. Let's use that same type of thinking with a parent quadratic, which I will start sketching in green. The good thing about those is that those, for me, don't have to be as smooth, but or I'm sorry, as perfectly drawn graph like the lines where I use my tools. But that's a pretty accurate graph, right? Of y equals x squared where it goes through the origin. So the way we want to think about this is, all right, for the graph in yellow, the parabola in yellow, y equals 2x squared. We haven't really done something like this, but using the same type of idea, what's happening to the parent graph when we multiply it by 2? Did it seem to get larger or smaller? It got larger y values, right? They became larger. And because these are all positive, they're always going to become larger y values. By what factor? By 2, except at the origin, because 2 times 0 is still 0. But whatever this y value was here, when for the new graph is going to be twice as large. Whatever this y value was here for the new graph is going to be twice as large. So hopefully you start to visualize that. The green graph is getting stretched vertically. So some form of that. Those will not intersect at another point except the vertex. Right, but hopefully you're starting to see the original parent graph became the yellow line by being stretched vertically. The y value is being stretched vertically, and because of symmetry, we have the same thing going on the left side. The y values were being stretched vertically as well. That's the main idea, and therefore, what do you think is going to happen when we have y equals 3x squared? Where would it fit between the system of equations? Is it going to be between the green and the yellow parabola, or is it going to be under the green line? Absolutely not, because it's times 3, and that's going to be 3 times as larger as the original parent graph, and a little bit larger than the graph in yellow. Hopefully that makes sense. The y values are being stretched. The larger that number gets, the larger that this coefficient gets, then the steeper and more vertically stretched it's going to get. All right, and the main format, if you want to compare it to y equals ax, where a is a vertical transformation, this is a vertical stretch for now. In this case, it's a vertical stretch, it looks like. It's not always a stretch, but then we can have the same idea, y equals ax squared. Where it looks for right now, this is a vertical, same thing, vertical stretch. I won't write it because I already wrote it one time, but you get the idea. We will think of that a term or coefficient as a vertical stretch. Sometimes it's called something else, so let's explore it. And remember that the a term can sometimes be negative, meaning all of these would reflect down here vertically. We've seen that before many times. We have experience with that one. All right, so there's the idea. All right, next we have down here, same idea of starting with linear equations, the parent graph y equals x in green. So you try and visualize what that looks like or plot it at your own pace. I will check that now. Starts at the origin. The slope is 1 over 1. So just like before, it's going to be up 1 over 1, up 1 over 1, 3 times. I'm going to go to about right there. By symmetry, we should have that point. And see how quickly I can do this. That's not too bad. I like that. All right, next thing in yellow, or next line in yellow, it is y equals 1/2 x. The slope is up 1 over 2. All right, so same thing, starts at the origin. This is the only thing they have in common, but up 1 and over 2. Up 1 over 2. Up 1 over 2. By symmetry, should be that point. I'm going to remove that. Let's see. Which one is increasing at a faster pace? The original parent graph or the new transform graph with a slope of 1/2? And the same idea, what would happen to the blue line that we're going to sketch for y equals 1/3 x? Made a mistake there. All right, let's fix that. So the last line I'm going to sketch is y equals 1/3 x, but it also goes through the origin. We know that, with a slope of up 1 and over 3. And by symmetry, it will have that point. Let's connect those dots with a straight line. Something like that. That's pretty accurate. But the idea is, all right, same as before, parent graph is in green. How did the parent graph become the one in yellow? Notice that it wasn't shifted up or down. It wasn't shifted to the left or to the right. It seems to have either, was it stretched, however? No, it wasn't stretched. The term for before stretch implies that it got longer, that it got a larger Y value. But this one is not stretched. It became smaller. Think of something that means the opposite of stretch. It got compressed. All right. So I want us to think compression. Compression. Here's how to spell it if you're not familiar with the term compress. It became smaller. How did the blue line become transformed from the original parent graph? Did it become stretched? Obviously not. It became smaller, or we think compressed. All right. That's what we want to think. Compress. And apply that same type of thinking to, again, parabolas. But now the parabolas will have fractions like 1/2, fractions like 1/3. What was the fraction, or what is the number that's implied for x? It's 1. Remember that. For the other one, it was also 1. And we start to think, what happens to the graph when the a term, what is going to happen when the a term is positive, meaning it's greater than 0? No, not positive, not greater than 0, I'm sorry. When it's greater, if it's 1, it is the parent function. If the a term is 1, it is the parent function. What happens if it's greater than 1? It got stretched, remember. It got stretched. So when the a term is greater than 1, the function, whether it was a line or whether it was a parabola, it got stretched. And the idea here is, what happens when the a term is less than the parent function, than the coefficient of the parent function? So when the a term is less than 1, if it's equal to 1, then we get the parent function. But look at these fractions. They all happen to be smaller than 1. And it doesn't have to be 1 over 2. It could be something like 4 over 5, which is still less than 1. All right. So think of that idea. When the a term is less than 1, then we say that it got compressed. The y value got compressed. So either the graph got stretched or it got compressed. If a equals 1, then it is the parent function. If a is less than 1, we know the function got compressed, or the y values got smaller. And if a is greater than 1, the y values got larger, or the function became stretched. All right, that's a good way to think about those. And let's apply it to these parabolas. All right. So again, in green, I'm going to go with my parent function. Y equals something squared. It goes through the origin. Something we're familiar with at this point. Good. And now think of the, remember that, what was the a factor for this one? Because it is the parent function, it is a 1. Because these fractions are smaller than 1, then we know that every y value is going to get compressed. Rather than being higher above the parabola, they're going to be under the parabola, which means that those values got compressed from the original parent graph. And it might look something like that. Not 100% scale, but for what we're doing right now, this is great. Notice that 1 is larger than 1/2. Therefore, those y values got compressed by a factor. You can think divided by a factor of 2, you know? And then in blue, because 1/3 is even smaller than the previous, then we know those y values got stretched even more, making a parabola that's even more narrow than the previous 2. And that's the main idea for this practice. Remember that this a coefficient is now going to represent a vertical. Really, the actual term at the end, combining reflections and all, is not just compressed versus stretched. It's also it also implies a direction, which I want to write in important color, I guess. So let's write that in this color. So the a term, just to end this video, the a term is known as Here it is. You ready? Known as the vertical scale. The vertical scale. All right, so that implies also whether it was reflected across vertically. Implies the negative and implies the coefficient being a fraction or not. All right, so that implies all of the possibilities that can happen with the A term. All right, so not to make this any longer, this is the end of the video. If you're still listening, I'm not sure why, because maybe you should be practicing some more vertical scales rather than listening to me talk more and more and more. All right, but appreciate it if you do. I hope you hear me more on the next few videos, and have a great rest of your day.